back to my channel Infotainment and the play series of digital signal processing. Before entering into DSP, now that we have learned the way to remember Fourier series, Fourier transform and discrete time Fourier series, discrete time Fourier transform and their inverses, let us learn what is meant by sampling, truncation and extension. See, let us learn what is sampling. The sampling basically means to convert a continuous domain signal to discrete signal. That is, as the name itself suggests, I would obtain the samples of the signal at some discrete units of time. Okay, so this is the time axis. Suppose that I have a signal like this, okay, which I multiply by the train of impulses of magnitude unity, which is again varying with respect to time, and this is the amplitude, and this remains 1. Fine. When I multiply the product of this, I would be getting the samples. Say it is t over here again. When I multiply these both, the time instants at which I have these impulses will be the time instants at which I would be obtaining the value of this continuous signal. Say for example, I have an impulse at this point, then I would be obtaining this value, which is the value of the continuous signal. That means I am sampling this signal using the train of pulses. So this is how the sampling happens. So say for example, the same, it is like a kind of, we obtain the values in the form of discrete values. However, in the same way it just goes off. Okay, so similarly on the negative axis and so on, it just gets translated. Here there is a continuous signal, here you can see there is gap, and it is discretized at discrete units of time. So I know the amplitude at the discrete units of time. So this is about sampling. Now that we know what is meant by sampling, let us see what is meant by truncation and extension. Now, before learning truncation and extension, let us see the three kinds of signals. That is, the signal which is periodic. Okay, one is periodic, the other is non-periodic. Now, the moment I say a signal is periodic, it is understood that the signal is from minus infinity to plus infinity. That means it is infinite. But in the case of non-periodic, the signal can be finite and can be infinite as well. So there are two other classifications wherein the signal is finite or the signal can be infinite as well. When I say the signal is finite, that means the signal is defined only for a particular given interval, or I can say this is still a non-periodic signal because it is not defined from minus infinity to infinity. For a signal to be periodic, it has to be defined from minus infinity to plus infinity, and a non-periodic signal can also be infinite if it is a random signal like this, which continues up to infinity. Okay, this is the time axis and it continues up to infinity. So these are the three important classifications of the signal. Now, keeping this in mind, let us see what is meant by truncation and extension. In the case of truncation, the process, what do I do is, truncation involves the process of converting a periodic signal to finite non-periodic signal. As the name itself suggests, the term truncation means I am truncating a signal. Say, let us consider a sinusoidal signal which is defined from minus infinity to plus infinity. Now this is 0, this is pi, 2 pi, 3 pi, and so on. Okay. Now what do I do is, if I assume that this is t, which is the time period, if I want to truncate the signal only between 0 to 2 pi, I just write it as, this is the time axis, from 0 to 2 pi, okay, which is t. So the signal which was infinite and periodic, I have extracted a part of a signal. Now this signal is non-periodic and it is finite as well. So how do I represent this signal is very simple. See, the signal is periodic. So now if this signal is represented as x of t, okay, and this signal is represented as xp of t, then I can define this signal as x of t is equal to xp of t when t ranges between 0 to capital T and 0 otherwise. Okay, 0 otherwise. So this is how the truncation or truncated signal is defined. Now once we are done with the process of truncation, let us see the process of extension. In the process of extension, again the concept remains same. I convert a non-periodic finite signal to an infinite periodic signal. So how do I do it? Is again very simple. For example, if I take this signal which is defined from 0 to 2 pi, okay, if I consider this signal to be x of t and this is a time axis, if I take this to be the time period, okay, this signal is a non-periodic signal. Why is it non-periodic? Because the signal is not defined for t greater than 2 pi and for t less than 0. Okay, so hence it is a non-periodic signal. Now this signal, if I convert to an infinite periodic signal, then I can tell the signal is converted from a non-periodic signal which is finite to an signal which is infinite and periodic as well. Now we have seen how we represented the process of truncation. Now let us see how do I represent this signal. Okay, if this signal is represented by xp of t, now let us represent the process of extension as we did in the case of truncation. If I represent this signal as xp of t, now xp of t can be represented in terms of x of t as summation of x of some value. Let us see what that value is. Obviously t, okay, plus L into capital T, where L ranges between minus infinity and plus infinity. So if I represent this signal by x of t and this as xp of t, then xp of t can be represented in terms of x of t using this expression. The same thing can be represented in terms of discrete domain, that is, if I represent it as xp of n, that should be equal to summation L ranging from minus infinity to plus infinity x of n plus L into capital N, where capital N represents the time period in the case of discrete domain. Thank you very much for watching the video. Hope you have found it informative. If you have liked the video, then please press the like button. If you haven't subscribed for my channel, please subscribe so that you would be notified whenever I upload the next videos. Thank you.